Okay, so in this video clip, I'm going to take a look at some Python code that's been set up for Jupyter Notebook, and it's been posted here by Davis Edwards, and Davis has put on, so first of all, he's rated here as a pro, and I think the code that he's set out here is code that is linked to a textbook of some kind. So we have Python code for European options, Black-Scholes, Black 76, Merton, Garmin, Kohlhagen, and then spreads American options, Bjerksund and Stensland, which I'm interested in taking a look at, implied volatility, and Asian options. So there's quite a lot in here, and look, at first glance here looks really interesting type code. So let's just open up and see what's in here. And okay, so we've a range of data. So let's just see Python code containing closed form solution for valuation of European options, American options, Asian options, spread options, heat rate options, and implied volatility. And yeah, it's a book, Edwards, Energy Trading and Investing, Risk Management and Trading, Energy Investing Demystified. So let's just see if I can track this down. Okay, so we go into Amazon and then take a quick peek at if there's a textbook here. And there is, right? Energy trading, investing, trade, risk management, structuring deals, and also could be another book, energy. Okay, so it's a couple of editions. It's another author, looks like. Just check the Edwards. So energy trading and investing. And so there are two textbooks at least, with Davis E. Edwards, who is the author, right? Maybe just take a look at what's in there. Okay. Anyway, let's just go back and have a look here at what's going on. So we have just come down a little bit. There's okay, there's explanation of the different models, so maybe I shouldn't gloss over this too quickly. Generalized Black-Scholes, and we have Merton, Black 76, Garmin, Kohlhagen, and of course all these are kind of out of the same family. They're closed form solutions for European options, and there's an Asian option here, Asian adjusted volatility, a spread option, Kirk approximation, and I'm very keen to explore this, and heat rate call option. So it's looks as if it's based here on again energy, so price of electricity, price of natural gas. It looks like it could be two assets, and maybe there's some kind of difference between the two. So again, I wouldn't mind taking a deeper look at the content here. And then a model that I'm relatively familiar with is the Bjerksund and Stensland model 1993, and there's also the 2002 implementation. And I think we've got the link here to the 2002 implementation. And the formula for the model is set out. And then when we come down here further, okay, we get the implementation of the model. So that looks very interesting. And it's all there, right? Complete implementation. So I've already set this up in the Anaconda Navigator environment. I've launched the Jupyter Notebook, and the code is based on the Jupyter Notebook format, and we'll just come in here and we'll launch the Jupyter Notebook go into my OneDrive where I've already set out, implemented this code, and I just have to find, I don't think, yeah, it's this code, right? So basically, yesterday I went through the code. Now, the code that I have here, it's just simply copy and paste in. So for example, all I would have needed to do here is gone to the GitHub project, took the first segment of code that's here, just take this first frame and copy, and then went into the project and paste, and I paste all the way along, right? So the implementation that I have here is basically no alteration whatsoever in terms of the code. I just faithfully copied and pasted in from the Git hub portal here, and so in order to implement the code, then all we simply have to do is shift enter, and I'm holding down the shift button, hitting enter or return, and so on, right? And I keep doing that, and as we go through, then there's the different implementations of implied volatility using Newton-Raphson method. For the American option, using would appear a bisection technique, and so on. So as I'm hitting enter shift, the code is being loaded into the project. And again, there's Black 1976, which is popular for commodity futures and for bonds, but here I would imagine it's intended to be used for commodities and for energy trading. And Kirk 76, again, these models look very interesting, and I wouldn't mind taking a deeper look at them. So okay, so we're hitting shift and enter all along, and as we do so, we're activating the code, and there's a little bit of testing going on here, right, to check are the models consistent. I think he benchmarked against Espen Hoag's book to run this. Okay, so if we take basically here, up to here, just testing and just implementing the code and verifying or benchmarking the code against other models, right? So benchmarking. But if we actually want to estimate a Black-Scholes model, for instance, I could take the value here, 90, and this is the value of the asset. It's a call option, exercise 100, T is 1 year, risk-free rate 5%, volatility 20. If I shift and then, so hold down the shift button, press enter, you can see I get an estimate here for Black-Scholes model. That looks correct. I know if the asset price is 100, okay, I know if the asset price, so FS, if we set that equal to 100, and K, okay, so the code is being gobbled up here. So let's pause. So I have a value of the asset as being 100, exercise 100, time period 1 year, risk-free rate equal to 5%. If B is equal to 0.5, then that's B represents R negative Q. Q must be 0. Volatility is 20%. I hit shift, enter, and the value that I get is okay, so I've run into an error here now. We'll just go back and check that. So what I can do is I can take this Black-Scholes code here, and we'll just copy and capture the parentheses, copy, right, and come down here and just load it in again, paste, special, and we'll change this to 100. Okay, so what I've done is I've emptied the, just hit shift enter, it goes to 0. I've come up above here, I've copied a snippet of code from here, So this is the Black-Scholes. So I'll just copy. I'll come down and I'll just paste that in. Okay. And make sure that's working, and then shift enter and the code is working. I've then come here and I've entered in Bjerksund and Stensland 2002, and again if I change the value to be 110. Okay, so I'll just change this to be 110, hit shift and enter, and we get 1766. And then, so this is, I'm able to run these implementations then in Bjerksund and Stensland. I'll verify the results in a few moments. One of the interesting things here is that there's also American implied volatility, and I can set out, once I specify this, whether it's a call or a put in the future, the asset price, the exercise, the maturity, the risk-free rate, the cost of carry, and then put the option equal to the market value of the option. If I hit again shift enter, I'll get the implied volatility associated with this. So we can see here there's lots of very interesting formula. There's a lot of detail. When we go back into the GitHub portal here, we can see there's a lot of detail explaining the varying option models, and so a real kind of treasure of models implementation explanation here, and I look forward to exploring this a little bit further, maybe testing a little bit of the code and comparing back to in particular Espenhogue for the American options. But the values seem correct, in particular when I go into the implementation here. Again, using these variables, I know that once we have this combination of call, asset price of 100, exercise 100, time to maturity 1 year, risk-free rate 5%, if we set this equal to 5, that means the dividend is 0, the volatility is 20%, I should recover 1045. The option won't be exercised early because there's no dividend. So if I hit shift enter, I get 1045. That's consistent with the European option. Looks like this model is correct. I wouldn't mind testing a little bit more, but it looks as if everything is working well, right? And I look forward to testing this a little bit more, right? Okay, leave it there.